So now you've got a color-coded periodic table. In each of those color-coded blocks, you can always tell what type of subshell is being filled. And as to which subshell is being filled, there's a relationship between the period it's in and the number subshell. So I promised you would see the periodic table in a new light, and it makes sense in a way you never had before. Well, there's our plain old periodic table that you've been looking at your whole life, but with the sublevel blocks colored, the S, the P, the D, the F. Doesn't make any more sense that way than it ever did. There is the full, blown-up periodic table. So, if we look at first look at that first period, we've got 2 there. We start off with the 1s1, 1s2, 2s1, 2s2. 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. We go back over. I can't quite reach, but 3s1, 3s2. 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. We go back over to 4s1, 4s2. Then we fill 3d. How many elements do you think there are across a row of the D block? 10. Why? Because there's 10 electrons in the D subshell. So, 3d1, 3d2, 3d3, 3d4, 3d5, 6, 7, 8, 9, 10. And then we're back to 4p. 1, 2, 3, 4, 5, 6. We go through 5s, 4d, 5p, 6s, and then what are we filling? 4f. Now we're down to lanthanides and actinides. You'll notice that the D's are always one main energy level behind the period, right? The F's are a full 2 main energy levels behind the period because of those crossovers in energy level. So if you want to do noble gas notation for any element, all you have to do now is find the noble gas you're going to use by looking up to the next row, find that noble gas, and then you just go, okay, well, let's see. Let's do an example. Atomic number 44, ruthenium, named for who do you think? Ernest Rutherford. Yep. So, Rutherford. So, atomic number 44, what noble gas would you use? Krypton. Okay. So, krypton is in the 4th period. We start filling what next? 5s. So it would be krypton, parentheses, 5s2, and then 4d, 1, 2, 3, 4, 5, 6. Noble gas notation was never this easy before. That's easy. Because I want you to do the hard way first. Yeah, that too. But also, if you hadn't done it the hard way, you wouldn't get the easy way. Like now, when you've done it the hard way, people read the easy way and they go, oh, that's so cool! But yeah, they wouldn't do that if you hadn't done the right way first. You'd be well confused. So, okay. Okay. There are two, I said there were two problem children. And you notice we haven't colored helium on here yet. So helium and hydrogen, these are the original elements.
When did you start it? I saw it.
Okay, yeah, we do. We color helium with protease blocks. So helium and hydrogen are those ones that don't fit in to the family. They're the original two elements. They're the first elements, the proto-elements. And if you smash two hydrogens together, we said we get a helium. So hydrogen, its electron configuration is S1, which would put it in what group? Group 1. However, group 1 are metals. They're alkali metals and they're solids at room temperature. They're all these kinds of things that hydrogen isn't. So on electron configuration, it should be a group 1 element. We typically put it there. However, in terms of behavior, it behaves more like a group 17 element, which is why it appears twice. So it appears over, Dylan, this was your question, right? So it appears over group 17 because that's how it behaves. Now, helium, on the other hand, acts as a noble gas. But helium's configuration ends in what? S2, the noble gas is all left with what? P6. So, in terms of its arrangement, it should be group 2, but in terms of its behavior, it should be a noble gas. And why is it stable with 2 electrons? It fills its subshell. It's got a full outer subshell. So, yeah. So you can color helium the same color as you colored the S block, but know that it still behaves like a noble gas. So we now have that. Okay, we'll pause this.